Okay, I'm going to give a little series of 3 lectures about Module 11, and these are really designed for folks who skipped Module 10. If you've done Module 10, then you pretty much have seen all of this. Um, this lecture might be useful to you as an alternative way of viewing curved arrows and predicting reactions. Um, but for most people, this is designed for folks who haven't really used curved arrows before, maybe did Module 6 um, and got their intro to curved arrows there, but now we're going to apply it to reactions. Um, so the idea is this: in chemistry, um, we have reactions that happen, and you need to first identify, well, what's going on in a chemical reaction. Uh, Fundamentally, what happens during any chemical reaction? I want you to think about that for a second. All right, what did you come up with? Well, hopefully you identified that during chemical reactions, we break bonds and we make new bonds. All right. um, those are the two fundamental things that happen. Some reactions just involve breaking bonds. Some reactions just involve making new bonds. Most reactions involve both of those things happening. Um, so, in other words, when we break bonds, usually that means a shared pair of electrons is becoming a lone pair. It's not shared anymore, right? So this is when a bond becomes a lone pair. And we make new bonds. That's when a lone pair becomes a bond because now we have an unshared pair that's becoming a shared pair. That makes a bond. So chemists want a way to describe what's going on with those electrons. And so we've come up with uh, a language that we use to describe a shorthand to show how those electrons are moving, changing, getting shared, getting unshared during reactions. Um, so what we will do is we will use curved arrows. And when I say curved arrows, it means the arrow's got to have some curve to it. Sometimes it'll be a big loop. Sometimes it'll be less of a loop. Occasionally, I might draw an arrow that kind of does this because I want it to squeeze into a specific spot. Um, but we will use curved arrows. Okay. And the key is the arrow starts at a pair of electrons. Um, and there are two kinds of pairs of electrons. It could be a lone pair or a bond. And generally, it's going to end at an atom where those electrons are getting shared with, or where we're making a new lone pair. Um, one thing to note is that the end of my arrow here has two little arrowheads. Those arrows always indicate that we're dealing with pairs of electrons. Um, there are sometimes arrows used with just one little hook at the end. We call those fish hook arrows, and those show the movement of one electron. But this double hook indicates 2 electrons. So we call this the curved arrow formalism. Just to make you aware of some of the terminology that gets used sometimes, where the arrow starts is often called the source. And where it goes is often called the electron sink. I won't use those terms too much, but if you do hear them, that's what it means. The source is where your arrow is starting, and the sink is where the electrons are going. One thing to note, the sink, it has to have space for those electrons. You can't dump electrons into an atom that already has a complete octet without moving some other electrons out of the way to make space. So this is the curved arrow mechanism. And really, there's only 3 kinds of curved arrows. The first 2 are really straightforward, and the third maybe a little more complicated. But first type of move is when a lone pair gets shared with a new atom. We have a name for that. We call that bond formation, or we form a new bond. Right? A bond is a shared pair of electrons. So when you take a lone pair and you share it, you form a new bond. Sometimes you have a bond break, and those 2 electrons go to one of the 2 atoms that were formerly sharing them. So that's when a bonding pair, a bond, becomes a lone pair, right? So a lone pair becomes a bond, or a bonding pair becomes a lone pair. Those are the 2 most common types of arrows. Occasionally, what you'll see is a bonding pair that's between 2 atoms. You can call them A and B, and it moves and becomes a bond between A and a new atom, so A and C, or between B and C. So when a bonding pair becomes a new bonding pair, you're breaking an old bond and forming a new bond. So those are the 3 kinds of moves. I want you to keep that in mind. I will show you some common mistakes a little later, but these are the 3 kinds of moves. So first, a lone pair getting shared with a new atom. So I'll give you an example of that. Let's say I have a bromide ion. Bromide ion has 4 lone pairs. And let's say it comes across this thing, which we call a carbocation. Remember, a carbocation has an incomplete octet. So this right here, you can imagine, is a match made in heaven. If you imagine what the conversation between these 2 would be like, well, bromide would be like, hey, I've got extra electrons. And carbon would be like, hey, I really need electrons. So it's really, really a great match. So I like to personify atoms. So I imagine the bromide saying, hey, carbon, why don't I share this lone pair with you? Now, we're not going to draw voice bubbles in our reactions, but we can still think them. So I'm just drawing them there to show you my thought process. And when we do that, I'm going to highlight the lone pair that I'm going to share. I'm going to draw an arrow from this lone pair to this carbon atom. All right. I give my arrow a little curve. And now I want to describe, okay, what do the products of this step look like? Well, now I'm going to form a bond. I'm going to have bromine still has its three other lone pairs. I could have left those out if I wanted to. Carbon still has its three other hydrogens, but now that lone pair has become a bond. And I made that bond a little too long. I'm gonna shorten that up. Yeah. So that pair of electrons that I highlighted in pink was a lone pair, now is a bond. That's your simplest kind of arrow. In this case, the carbon had an incomplete octet, so I didn't need to make any space at the carbon. There already was space. So that's a really simple example. What about type 2, where we're breaking a bond? So let's imagine a different scenario. I've got a carbon with 4 bonds. It's bonded to an oxygen with a positive charge. One thing you might imagine in this scenario is oxygen. Oxygen's very electronegative. It's been kind, sharing this pair of electrons with carbon. But you might imagine oxygen deciding at some point, no, I'm going to be selfish. I'm going to pull these electrons back. So it might say, I don't want to share anymore. So what it might do in that case is take this bonding pair and just pull those electrons back to itself. Turn that bond back into a lone pair. So it's very similar to reversing the step that we just saw, because carbon now has a positive charge, and I've released a water molecule. So another common move is when a bond breaks. Now, most reactions are going to involve a combination of these two, where we're making a new bond and breaking an old bond at the same time. So you can imagine scenarios where you have 2 arrows. First, you share a lone pair, and then you break a bond at the same time. I'll show you what that looks like. So here's what a combination looks like. I might have Br minus. And I might have this molecule here. And I could combine those 2 steps. So I could have bromine share a lone pair with carbon. And at the same time, I could have oxygen pull these electrons back to itself. So I'm forming a new bond and I'm breaking an old bond at the same time. And it's not necessary to color code the way I'm doing it, but for instructional purposes, it might be helpful to color code. So here's my new bond that got formed from the pink lone pair. And here is my lone pair on oxygen that came from this orange bond. So that's a combination of breaking and forming at the same time. That will be much more common. I kind of broke them down into two separate steps on these two slides. You will see them more often in combination. All right, let me give you an example of the third type where a bonding pair becomes a new bond. Again, this is a little contrived, but to make things simpler, I'm going to show an example where I have an incomplete octet on my electron sink using this boron because that's got space to make a new bond, so I can just make the new bond without breaking an old one at the same time. But let's imagine I had these two molecules. These carbons, if we're imagining what their relationship is like, they're sharing these two pairs of electrons. They have a double bond. And that second pair of electrons, one of them is going to say, you know what, I'm breaking up with you and I'm taking these electrons and I'm going to go start a new relationship. So it's a little bit of a more complicated statement here. But this carbon over here says, you know what, I don't want to share with you anymore. I'm taking the shared electrons and sharing them with someone new. So it's got elements of this one where oxygen is basically like, I want to break up. I don't want to share anymore. I'm just going to take the electrons. And the first one where, one atom is sharing with another one. This one is really cold-blooded, where this carbon is like, no, I'm taking the electrons and I'm gonna take them somewhere else. I'm not just going to be selfish. So we take this pi bond here, this second bond, and now I share that with boron. Now, this arrow on its own, you might note, doesn't tell me which of the two carbons. I'll number them. Let's call this carbon 1 and carbon 2. It doesn't tell me which carbon is actually taking the electron. So the arrow itself is ambiguous and could lead to two different results. As you learn more reactions, you'll learn ways to tell which of the two carbons keeps the electrons and which of the two carbons is left without them. But that's a lesson for another day. So what do I get here? Well, my CH3 group over here still stays the same. I still have carbon 1, but carbon 1 is being left high and dry now. It's going to have a positive charge. Carbon 2 still has its two hydrogens, but now it's bonded to boron as well. Boron is bonded to three hydrogens. And if you're tracking where that bond went, it used to be between carbon 1 and carbon 2. Now it's between carbon 2 and boron. So bonding pair moving to a new bond, that's an example. So that's it. Those are your only three kinds of allowed curved arrows. Um, let me show you some of the abuses, some of the bad moves that people will try to do sometimes. And I would say the key is that electrons are not getting transferred in any of these reactions. So anything that involves transfer of electrons rather than sharing of electrons is not allowed. So do not transfer electrons. That's what happens in ionic bonding, where one atom steals electrons from another. In these organic reactions, most of the time, electrons are not getting stolen, they're getting shared. Um, so, a mistake that someone might make, if we go back to this original example with the bromide ion and this carbocation, um, sometimes people will see this arrow and think, oh, those electrons are jumping from bromine to carbon. And I want to emphatically say, no, do not do this. So the key idea is share, don't transfer. Now remember, this arrow shows that bromine is sharing that pair of electrons, forming a new bond. So you should never have a lone pair go from one atom to another atom. A lone pair can become a bond can become a lone pair, but a lone pair cannot become another lone pair. Never going to happen. You also wouldn't want to have two electrons just jump to another atom either, right? You wouldn't want to have a bonding pair jump to another atom. So if I had a molecule like this, where I had a bond there, a double bond there, and I had this arrow here, I would not want to just transfer those electrons to the third carbon and leave both of my prior atoms high and dry. Definitely not that. Again, the theme is share, don't transfer. So if we were to have this situation, the actual products would look like this. I would share that bond. This bond would now become a bond between two new carbons, or one new carbon, and one old carbon. So notice if I label this carbon as blue, the electrons stay with the blue atom. So the shared electrons can never leave both atoms. They have to stay with one of them. All right. So the theme is share electrons, don't transfer electrons. All right, one last note, and I already alluded to this, but in most cases, when you form a new bond, you need to break another bond at the same time to make space. So let's imagine these two molecules approaching each other. Um, this OH minus oxygen has a negative charge, so it's got some extra electrons. We can imagine it saying, like, hey, carbon, let me share. Right? So, same voice bubble that I did before. And again, you're not going to be drawing voice bubbles, but I'm giving you my thought process. So, oxygen decides, okay, I'm going to share a lone pair with this carbon over here. Uh, what would that make if I just did that? Well, I would be forming a new bond between oxygen and carbon. Carbon still got two bonds to hydrogen, still got a double bond to oxygen. Um, and hopefully, this makes you a little sick to your stomach. I'll give you a minute to think about it. And hopefully you saw that, oh, this carbon now has 5 bonds. So this is over an octet. So that cannot happen. Uh, so there's generally going to be a second step where, carbon responds, all right, hey, oxygen, I would love to share with you, but I need to make some space first. And how is it going to make space? It's going to make space by taking one of these two bonds and moving it up onto the oxygen over here. So what will that actually give me? That will give me now carbon has a bond to the new oxygen. This one came from that pink pair of electrons. Still has one bond to the old oxygen. Now, this oxygen has the negative charge. So we formed one bond and we broke one bond. So that's going to be your most common scenario. All right. Last thing now to do is look at a couple examples. And then next time I'll talk about how we could predict when two atoms might form a new bond or when a bond might break. So here are two examples. I've given you curved arrows. I want you to draw what you think the products would look like. And if it helps, I can color code for you. But take a few minutes to think about what the products of each of these two sets of arrows would look like. So pause, draw what you think the products look like, and then come back. All right. Hopefully, you went ahead and made your prediction. So in the first case, I would still have my N triple bonded to C. Nothing has happened to that. I still have my C bonded to 3 H's. Nothing has happened to any of those bonds. But now I have a bond between the two carbons. And bromine is now on its own. And it's going to have a negative charge. I hadn't drawn in before all of the other 3 lone pairs on bromine. Remember, lone pairs can be implied, but bromine still has those other 3 lone pairs, and now it has this orange one, which used to be a bond. In the second example, I still have carbon. It's still bonded to 2 hydrogens, but the OMe group has broken off. And now, instead of a single bond here, it's got a double bond. And my OMe group had 2 lone pairs. And now it's got 3. So it's got a negative formal charge. And that's going to do it for this first segment of the Module 11 lectures.